Oh, okay. Got it. Okay. Yeah, great. Yeah. All right. Today, yeah, we're extremely pleased to have Zurab Guguchia. Did I spell your name correctly?
Yes, yes, yeah, precisely. Yes, thank you.
Okay. Yeah. So I mean, I know him for quite a few years, even when he was a postdoc with Tomo Yomura's group. So from which this series originally started. So Zurab got his PhD degree from Zurich in Switzerland in 2013. And then he's been doing a couple of postdocs at Princeton and Columbia. And now he's a tenure track faculty member at PSI. So he has done some, very interesting MUSR work on the different magnetic materials from which, I think a lot of the audience are going to be very much interested. So they are welcoming you to give a talk here. Yeah, thank you. So it's all yours.
Thank you very much. Thank you, Printek, for the introduction, and thank you for the invitation. So I have a long program today. So I will talk about the Muon spin rotation insight into the topological kagome magnets and kagome superconductors. So the first part of my talk will be about the connection between the topological Hall conductivity and magnetic competition in these kagome magnets. And then second part of my talk again will be about the kagome magnet, but to find some low temperature magnetic crossover, which is linked to this quantum limit churn phase in the system. And last 15-20 minutes I will spend on this magnetic evidence for the time reverse asymmetric breaking state in this topological kagome superconductor. I would really thank all my collaborators from different places. It's really a large collaboration. I'd like to thank the bulk MUSR group for this very nice teamwork from PSI, and Laboratory for Developments on Methods for providing nice samples and doing some characterization measurements. Also the neutron scattering lab doing different types of neutron experiments. And I would like to thank my close collaborator, Professor Zahid Hassan, Jashin, and other members of Hassan Group for a very productive collaboration and a very nice exchange of ideas. And I would like to thank theorists for the theory supports, and seeing the crystal, very nice crystals came from different groups from China. And I would like to thank all the people for bringing their knowledge and expertise around this project, which made it successful so far. I'd like to thank everyone. Okay, so let me start with the first subject, which is this cobaltine sulfur. Here's a mistake, doped with indium. Okay, the main motivation of this in topological magnets was to study the interplay between two interesting properties of quantum materials. This is magnetism and electronic topology. And the basic idea is to have magnetically induced topological system, and then by controlling the magnetic properties to have control of the topological invariance or topological transport. And so combining the strong correlations into this spin, with the spin orbit coupled, strongly spin orbit coupled materials, we can get some new concepts and new concepts related to phases of matter, but also it would give us some knowledge about some future applications of the materials. And along this line, there are several kagome magnets which appeared as the most promising systems. And I will today talk about these two, to give two examples here. And I cannot list all the works, but these are the recent papers related to these topological kagome magnets. Yes, but today I will mostly concentrate on the local probe, local probing of these magnetic properties in the kagome magnets, and using the Muon spin rotation technique. So the material which I mentioned here, the cobalt, is the Well semi-metal candidate, and I want to make some general introduction for the students about the Well semi-metals. So as you know, the Well fermions is very, plays an important role in the standard model, and they are considered as a building blocks of fermions in quantum field theory. But the experimental observation of this Well semi-metal, tantalum arsenide, was in 2015. So the Well semi-metal is a system in which you have where the low energy quasi-particle excitations are Well fermions. So in Well semi-metal, you have the so-called wild nodes in the bulk, where two non-degenerate bands cross, and they are separated in momentum space. They come in two flavors, so you can have a left or right-handed well fermion, or the different, positive or negative chirality. So you have some kind of 3D version of the Dirac fermions. And if you imagine the massless Dirac dispersion, if you split in two, then you get the wild fermions, so the wild dispersions. And the topological protection comes from the separation of these dispersions in the momentum space. So they're topologically protected states in the bulk. So in addition to these wild nodes, we have this so-called Fermi arc states, which is a disconnected Fermi surface. And the combination of the Fermi arc and the wild nodes make the system exhibit topological ground state. It's really a 3D is a topological. So it makes also easy to study with a bulk probe, such as neutron or muons and so on. So we are not limited only on the surface. So it extends the topological classification beyond the topological insulators. So each well node can be thought of a monopole source or a sink of the quantity, which is called Berry curvature. So in the Berry curvature is kind of imaginary magnetic fields. It's a magnetic field in the momentum space, which can be very intense. And it's directly linked to this periodic part of the Bloch wave function. And if you have a time reversal or inversion symmetric crystal, it is 0. There's no Berry curvature. However, if you break one of them, then it can come into play and it can be very intense. And then it changes the electron dynamics, and it can produce a large Lorentz force on the electrons and so on. And the experimental quantity where the effect of the Berry curvature on the electron dynamics can be seen is the Hall effect, anomalous Hall effect. And the anomalous Hall effect, the intrinsic part of the Hall effect, is integral of the Berry curvature throughout the Brillouin zone. So it's directly linked to the topological properties of the Bloch states. And so in this whole conductivity, one can have some extrinsic part of the conductivity and the intrinsic part. And this extrinsic is related to some scattering effects. However, the intrinsic one, as I said, is directly related to the topological properties of the bands. And idea is that if you have a large, so the one way to find semi-metal candidates is to look for the systems which has the large intrinsic anomalous Hall conductivity. And this is so it's through the Berry curvature. So now regarding this the system Cobaltine disulfide, so it has the kagome lattice, and we have these corner sharing triangles of Cobaltine layer. And so this kind of geometry of the lattice attracted a lot of attention, as many of you know, because it offers the interesting band structure, and also the antiferromagnetic interactions on the layer is frustrated. So it can favor spin liquid phases or frustrated antiferromagnetic, non-collinear antiferromagnetic orders. So in this lattice, one can find the flat bands, and if you find the flat band near the Fermi energy or Fermi level, then because of the high density of states, it can hint at some correlated electronic phases. You can also find the Dirac dispersion like in graphene. So all these interesting band structure properties and plus this frustrated magnetism makes this lattice attractive for the physicists. So this particular compound has this ferromagnetic autoplane ferromagnetic ordering. At least it was reported that below 170 Kelvin, it should have the autoplane ferromagnetic ordering. And the original DFT calculations have showing that this is a half metal. So the low energy states around the Fermi level are all spin majority states. And you get this kind of band crossings near the Fermi level. And these band crossings form some kind of nodal ring in the mirror plane. And this nodal ring, if you include the spin orbit coupling, then it gaps out, but one pair of band crossings still remains. And these are the wild points near the Fermi level. So this kind of nodal ring or the wild, nodal ring or the wild points make this system exhibit topologically non-trivial band structure. And you have this large Berry curvature across this nodal ring. In addition to this, the nodal ring, the group of Zahid Hassan have shown that you have this kind of, in the STM, there is a pronounced peak at the Fermi level, which have shown that it arises from the kagome band, which is degenerated with this parabolic band. And with a spin orbit coupling, you can make a gap here and produce some non-trivial Berry curvature. And in addition, they've shown that there is some kind of unusual diamagnetic signal related to the bands. So to make the long story short, what I wanted to say is all these topological points, line nodes or the flat bands, concentrate this Berry curvature. And so you expect a large topological Hall response in this material. And this is indeed what was seen experimentally. So you see here the Hall conductivity as a function of temperature. It is relatively constant up to about 100 Kelvin, and it goes away upon reaching this magnetic transition temperature. And here, the value, it is relatively high value of the Hall conductivity, is about 1000 inverse on centimeter. And when the calculated value, which comes from the intrinsic part, so the Berry curvature part of the Hall conductivity, matches very nicely to the experimentally observed one. So this led to the conclusion that what is observed experimentally is really the intrinsic, the bend, the Berry curvature related Hall effect, so it's topological Hall effect. Also, if you take the ratio between Hall angle, the Hall angle, which is basically the Hall conductivity divided by longitudinal conductivity. So this Hall angle is very high for this material. It's much higher than for other the Hall effect materials. And so that's why we're excited to find a system which has both large anomalous Hall conductivity and giant anomalous Hall angle. And what is important that this Hall effect physics is really connected to the intrinsic band Berry curvature effects. So when we decided to look at on magnetism, to look on microscopic level and to see what is the magnetic structure and if there are any connection between magnetic structure, magnetic properties, and the topological properties. So for this, we used the local magnetic probe, which is called Muon spin rotation, and Muon probes the local magnetism within the unit cell. So it sits at the interstitial site, and it can probe its local magnetic environment. Also, at the same time, you can also probe the local magnetic response of a superconductor, either Meissner screening or the flux-line lattice. So we can extract the local field distribution inside the superconductor in the vortex state. And I will give some more, more extended explanation for this. Just for the students, so Muon is an elementary particle, which is 200 times heavier than electron mass, but 9 times lighter than proton. And so it's a heavy electron with a spin of 1/2. There is no quadrupolar moment. So basically Muon interacts only with the spin, and there's no direct coupling between the Muon and the quadrupolar moment. And it is a radioactive particle, so the mean lifetime is 2.2 microsecond. And it has this interesting parity violation, which we use then in the experiments. So we get from the accelerator, we get a spin polarized Muon beam, 100% spin polarized Muon beam. So we know where the Muon spin is pointing, and then they are implanted into the sample, and then they decay into positron and 2 neutrinos. The positron is that we are interested in, and then we count the number of positrons as a function of time. And so this is how the histogram looks like. So this is the number of positrons as a function of time, and it is a combination of the exponential decay, which comes from this radioactive decay of the Muon, and then we have these nice oscillations, which is a Muon spin precession around the magnetic field, can be internal or external. And so this is the most interesting part, which is the polarization. So time evolution of the Muon spin polarization. And the typical Muon signal looks like this. So we can extract, so the damping of the signal is the width of the field distribution, which gives us the information about a static field distribution or some dynamics, so dynamic spin fluctuations. And the frequency is proportional to the local field at the Muon site. And this field is proportional to the moment size inside the system. Now, if you have a magnetic material, depending whether we have uniform ferromagnet or non-uniform ferromagnet or the phase separation, we expect different time spectra. So if you have uniform magnet, then you have no damping at all, and then the frequency is proportional to the moment size. If you have this non-uniform, the different domain distribution, this is causing the damping of the spin polarization, and this is a proportional to inhomogeneity. And if you have phase separation, then the amplitude of the signal is reduced, and and you see it directly on the spectra. So by carefully measuring the MUSR spectra at different temperatures or pressure and so on, we can extract separately the information on the magnetically ordered volume fraction and the ordered moment size, which is advantage compared to neutron diffraction. And we can also learn about magnetic field distribution or magnetic fluctuations inside the magnetic material. There's many advantages of MUSR, but I would say what we used in these topological magnets is that it is very sensitive to small moment magnetism. So you can measure a moment as small as 10 to minus 3 mu Bohr, and you can measure short range magnetic ordering. So we can determine moment and volume fraction separately. And the fluctuation time is also complementary to the neutron scattering. Something that can be fluctuating for neutrons is muon is static for neutrons, so we can look at slow magnetic fluctuations. And we don't need to polarize the muon spin, we don't need any applied field, so we can just do measurements in true zero field. Okay, so these are the instruments that we have at PSI in the muon spin rotation group. These are 6 different instruments, and one is the low energy MUSR, which is used for thin films, and then 5 instruments which are for bulk materials. So we have the unique high field instrument, which can go to 9.5 Tesla and down to 20 millikelvin. We have the unique high pressure MUSR instruments that also we can go to low temperature and pressure of 2.8 GPa. And these are unique, and also low energy MUSR, the only place that one can do at PSI. There's a new instrument, also flame, for high longitudinal field and transverse field and low temperature measurements. So basically, we use all these capabilities now to study the materials that I'm talking about. So we have quite few unique instruments in the world. Okay, let me show now the results. So again, so we started with undoped compound. There's no indium so far. And now I show you time evolution of the muon spin polarization. So this is a typical signal which you see in the paramagnetic state. It's 180 Kelvin. And then if you lower the temperature, you see this already appearance of the oscillations, which is the appearance of the long range ordering. And then we lower the temperature and we see again oscillations with bigger amplitudes. So which means that large volume fraction. And finally, let's say if I look the signal at 5 Kelvin, you have a very low damping of the signal and a nice oscillation, which means that we have homogeneous magnetic ground state in the system. And so if you check with neutron diffraction here, I want to pay attention to the fact that the moment size is relatively small. So we could basically take upper estimate of the moment from this ferromagnetic structure. So with neutrons, we proved that the low temperature structure is ferromagnetic with this small of small moments, and this we only get actually by fixing by refining this diffraction pattern only with a c-axis moment. So we get this 0.2, 0.3 mu Bohr. And I show you that we estimate it with muons also, it's even smaller. But at least the base temperature structure is a ferromagnetic. But now what happens when we go higher in temperature? So if I record this spectra, so this is a Fourier transformation of the time spectra, and this is exactly the measured field distribution. And so at the base temperature, you have a narrow signal, so you have homogeneous fields, more or less. And then when you increase the temperature, you have the evolution of the second peak, which then becomes more or less dominant. So if you try to model this data, you see that we need to include the second component already from 100 Kelvin, and then this takes majority of diffraction up to the highest if you go close to a magnetic transition. So now if I plot the fraction of the component 1, so you see it is more or less constant, and then you lose this component, while at the same time, at the cost of this red, you get this component 2. And then it takes majority of the fraction. And then also it disappears like 2-3 Kelvin earlier than this red component. So if I plot the total magnetic fraction, you see that if you just look at the magnetic fraction, there's nothing interesting happening, but clearly you have these two intrinsic components in the system, and you have a large temperature range where these two magnetic components coexist. So I can now distinguish 3 different temperature regimes. So one is a ferromagnetic below this TC star, And then we have a large temperature range where ferromagnet coexist with some other, or phase separates with some other novel magnetic state. And then finally it goes into paramagnetic state. So the fact that we have a large temperature range with some phase separation between two states was already a new insight into the system. But now we of course need to understand what is the second magnetic state. But before I address this question, I want to show you already what type of correlation we have between these two distinct magnetically ordered regions and the topological Hall effect. So here I plot this anomalous Hall effect measured at two different samples. They match nicely to each other. Now, if I plot the ferromagnetic fraction on top, you see clearly the temperature evolution of the ferromagnetic fraction scales very nicely to the temperature evolution of the anomalous Hall conductivity. And I can also make this plot of conductivity versus ferromagnetic fraction, and you get a very nice linear correlation between these two quantities. So what we have this striking correlation between these, two like topological quantity and the magnetic fraction, and which means that the novel magnetic state actually suppresses the Hall conductivity, and that the magnetic competition between these two structures drives the thermal evolution of the topological Hall conductivity. So this quantitative link between these two quantities was very exciting to see. Now, to understand what is the magnetic structure at high temperature, so we considered highly symmetric magnetic subgroups, and then with DFT calculated the energies of such structures. So there's two such a magnetic subgroup. So one is when you have a spin, you have both out of plane and in plane components. So when spins are fully in plane, then you get this in plane antiferromagnetic state. Otherwise, we get this fully out of plane state. And then there's a second magnetic subgroup that has this 120-degree antiferromagnetic ordering. And this is how it looks like on this kagome lattice. So according to DFT, the lowest energy configuration is the ferromagnetic one. And this has energy about 20 millielectron volt per cobalt, higher than this one. But this means that the energies are not very much different. So these two energies are relatively close. And then the idea was, okay, when we increase the temperature, maybe thermodynamics somehow changes this balance between these two structures, and then somehow it favors the in-plane antiferromagnetic state. But to check this hypothesis, we did first we calculated the Muon stopping site because we had to know where the Muon sits, and after quite some work, we find that there is only one Muon site at this Wyckoff position, and so this is basically very stable site. So once muons are trapped, are really stops in this position, then it is trapped there, and it does not really move when at high temperature. And we also find that in each of the considered structures, ferromagnet or antiferromagnet, muon site is magnetically equivalent, which means that in both magnetic structures, we expect only one magnetic peak, or the one peak or one frequency. So after knowing the Muon stopping site, then we did the local field simulation considering these two different structures. So, and what we find that the base temperature spectra can be well described by this out-of-plane ferromagnetic state with a moment size of 0.14 μBor, while in the high temperature state, you can one can model it by combining this ferromagnetic state and the antiferromagnetic state with slightly different moment sizes. So it lines up with the data very well. And even we can follow, based on the simulation modeling, we can follow nicely the temperature evolution of this small moment size, 0.14 and 0.15 μBor. And then we find the two different transition temperatures for these two different structures. So this Muon stopping site calculation, local field analysis show that the high temperature structure is its in-plane antiferromagnetic state, and then we have a large temperature range where these two structures kind of coexist or compete. Now, how we can now understand the suppression of the Hall effect? So in that case, using DFT calculation, if you calculate the Hall conductivity, the intrinsic topological Hall conductivity, you see that for this structure, it has really the maximum value. It's about 1000, which you get experimentally. However, in this structure, the topological Hall effect is completely zero. So somehow you may have the wild points or nodes also within the structure, but they are distributed such that the integral of the Berry curvature is 0, so it gives a 0 Hall anomalous Hall effect. And then, of course, having in mind that this whole conductivity is dominated by this ferromagnetic structure, one can understand the scaling because we have kind of appearance of these antiferromagnetic domains or antiferromagnetic fraction, and then the whole conductivity also goes away. So what we have shown here clearly that we can tune the competition between antiferromagnetic and ferromagnetic structures, and then control the topological Hall effect by controlling this Berry curvature integral to Berry curvature. So we call it thermal tuning of the topological Hall conductivity. Okay, so the final phase diagram which we proposed is that we have autoplane ferromagnet and then this new antiferromagnetic state at high temperatures. And there was later on there was a theory work that analytically could reproduce. I'm not really expert, but could reproduce this high temperature XY antiferromagnetic state, so the 120-degree antiferromagnetic ordering, and they could also show how whole conductivity can smoothly evolve, decrease when this spins develop the 120-degree ordering. So we now, instead of temperature, we decided to apply pressure, which is a kind of quantum tuning of the system. And we saw that the effect is only at 20 Kelvin, so you can reduce the magnetic transition temperature by 20 Kelvin. So much stronger effect was by magnetic field. So less than 0.1 Tesla is enough to fully polarize the spin along the C direction. Later on, there was the group from China who extended the pressure studies at up to 20 GPa, and they have shown that this ferromagnet plus antiferromagnetic state is stable up to like 20 GPa. And the ferromagnetic also stays stable up to 20 GPa. And so, of course, when you apply pressure, you compress the system, and it seems like this compression does not break ferromagnetic state until very high pressure. But instead, what we did, we studied the indium doping effect. So in case of indium doping, we are putting some carriers. So we dope the system, but at the same time, we also kind of expand the lattice. So it's opposite effect than hydrostatic pressure. In that case, if you follow systematically the field distribution at different doping and temperature, we see that when you go to higher doping, we have this kind of field distribution, which is similar to the which we explained by this incommensurate helimagnetic ordering, similar to MnSi, manganese silicide. And this incommensurate helimagnetic ordering remains also at the highest doping level. So if I, without really telling you all these details of the measurements or the analysis, we can summarize now the data in a temperature doping phase diagram. And we can see that as a function of indium doping, we get much richer phase diagram than with pressure. So we can suppress the ferromagnetic state at very low indium doping. And then we have the mixed phase, antiferromagnet plus ferromagnet. But finally, then we end up into this helimagnetic state, and then we have only in-plane helimagnetic, incommensurate helimagnetic ordering in this system. So we have so within like 0.3 concentration of indium, we are suppressing this both antiferromagnetic and ferromagnetic state, and we end up into the in-plane helimagnetic state. And at the same time, if you look in this intrinsic Hall conductivity, you see that in this in-plane state, Hall conductivity is nearly 0, and we get some kind of non-monotonous behavior within the state where we have mixture of phases. So we can control the Hall conductivity by tuning this competition and by moving the system into this helimagnetic state. This we call like a quantum tuning of the topological Hall effect. So at the moment, we don't fully understand the peak here, why the Hall effect has a peak, but it could be related to some kind of charge transfer between these different magnetic regions. So maybe we have more charges on the ferromagnetic state coming from antiferromagnetic state, and then the Hall effect would increase because the density of the electrons would increase in the ferromagnetic regions. But this is something that we need to work more to understand. But at least we can have very efficient tuning of the magnetic competition by indium doping. Okay, so probably I will skip this. Yeah, so to conclude this first part of my talk, what we have seen we show the evidence for the volume-wise competition between ferromagnetic and antiferromagnetic orders in this Will semi-metal candidate. We saw a quantitative link between topological Hall conductivity and ferromagnetic volume fraction. We can very efficiently tune competition between these two order parameter by indium doping, and then we find these rich multiple phase transitions in the temperature doping phase diagram. And so we find the system where through controlling the magnetic interaction, we can tune the topological transport. Okay, now the second part of my talk is about this low temperature magnetic crossover in this terbium-166 kagome system. This is a project of my PhD student at PSI. So different from the cobalt compound, here we have two magnetic sublattice, and it's terbium, and there's a pristine manganese kagome lattice. And back in 91, it was shown that the system has large, like high magnetic ordering temperature and some spin reorientation at around room temperature. So it is kind of room temperature magnet. And the group of Zahid Hassan have identified this system as a new topological magnet. So what does this mean? I'll just list some observations that was reported in this paper 2020. So they see a quantum oscillations from relatively low fields of about 7 Tesla, which reveals the Landau quantization. And then by analyzing this Landau fan structure, they found this spin polarized Dirac dispersion and the large Chern gap in this system. They also find the large animal soul conductivity that comes from the Berry curvature fields, and also the quasi-linear magnetoresistance that comes from the was explained to come from the linearly dispersive, polarized bands. Okay, so now if I summarize what was found as a function of temperature so here I plot the animal soul conductivity, and also we have this large magnetic ordering temperature near room temperature. The whole conductivities at different samples, measured at different samples, they coincide nicely at high temperature, but somehow their behavior at low temperature is influeed by some transition, which was not known before. And some samples even can go even higher, show high values. And also if I plot this magnetoresistance at 8 Tesla, it has a sign change across 100 Kelvin and then large increase of magnetoresistance at low temperature. And also the quantum oscillation amplitude, which reveals the Landau quantization in this system that's related to this Chern gap, it also increases below about 25 Kelvin or so. So while the real magnetic ordering is at near room temperature, these interesting topological features appear only at low temperatures. And so the idea was to see whether there is some additional magnetic transition at low temperature, or why this is confined really and what's really going on with this animal Hall conductivity. So we again did the detailed measurements of the field distribution inside the system, and what we see is that at high temperature we have very low frequency component, and then we have transition to this higher frequency component that continues up to down to 1.8 Kelvin, but then you have appearance of extra components below about 20 Kelvin. And then again, you have this kind of the competition between these two components. So if I summarize here, this is internal field as function of temperature. So we see this kind of spin reorientation transition, which was actually reported previously from neutron diffraction. So we see here in plane fields, and then below 300 Kelvin, the internal field is pointing along the z-axis. And so for this, we had to do experiments to look the anisotropic behavior. So we have like 4 different positron detectors, and depending in which direction the internal field is on the sample, so we can basically, if the internal field is along the z-axis, then we see the more amplitude on, like the large amplitude of up down, and there's no signal should be coming from forward backward. So this kind of measurement single crystal, we can see the direction of the internal field. And this is what we used here. And so we have the outer plane fields, but then we have another frequency below this 25 Kelvin, which is higher than the frequency which we got at room temperature. And also interestingly, we have this, again, the volume-wise competition between these two components below 25 Kelvin. Okay, so if we would have these out-of-plane fields, which is truly static, then we should not see any signal or no depolarization on forward-backward detectors. But instead, what we see a strong depolarization, no oscillations, but we see this strong damping. And if you follow the relaxation rate as a function of temperature, you see that the relaxation rate of this dynamic signal. So this means that you have some kind of magnetic fluctuation, some dynamics, which is involved in this magnetic ordering. And then we have this relaxation rate is more or less constant, but then below 120 Kelvin, it increases. And this is a slowing down of these slow fluctuations, magnetic fluctuations. And then below 25 Kelvin, we see a strong reduction, and also the amplitude of the signal starts to reduce below this temperature. So this is a temperature below which we see also the additional frequency. So it seems that the fluctuations become static enough that on MUSR we detect this, precession, coherent precession, and yes, and then we enter into the static regime. And the difference between the internal fields means that, so if you now have the fluctuations which is beyond the time window of MUSR, then the MUSR would take a snapshot of the structure. So it's like time average structure. So it seems that the time average structure here is different than the real static structure here. And to see more precisely what kind of structures we have, we did again muon stopping site calculation, and then we estimated the dipolar field at the muon site by summing up all these dipolar moments in the large supercell. So, and the moment sizes we know from neutron diffraction, which we measured exactly on the same crystals. We find that dipolar field, if you assume the fully C-axis aligned structure, is about 1.4 Tesla. So it shows that it's a C-axis aligned field at the muon site, which agrees with experiment, but it also, the value agrees very well with experiment. I mean, it's pretty close. But any kind of, this kind of structure that we calculated, and any type of counting of the terbium and manganese would result a lower local field at the muon site. So from this, we concluded that this highest frequency structure which we got at low temperatures here, this is a C-axis static structure, C-axis aligned static structure. And here we have some time average structure, which could be slightly canted, or it could also point along C-axis, but with lower moment size because it's dynamic. So it's basically fluctuates. So we say that only static structure, C-axis aligned structure, we get only at low temperatures, and it also kind of freezes, these fluctuations freezes into this C-axis structure, not directly 100%, but it is kind of, you get some static patches, and then which grows as a function of, as lowering temperature. And and as soon as we get the static patches, even at the base temperature, we don't have 100% C-axis structure. So it's kind of still grown patch, but not fully 100% static state. So if you do a simple magnetization measurements, you can also see at low fields, if you apply field along C direction, you see that there is a hysteresis below the 120 Kelvin, below which we see the slowing down process. And these magnetic fluctuations can also explain this, because in this region, when we have static domains in a zero field cooling system, minimizes the macroscopic magnetization. And as soon as we do a field cooling, then we align the domains. While in this case, we have this dynamic magnetic domains, and then the whole effect is kind of averaged out, so you don't register any hysteresis in the magnetization data. So these magnetic fluctuations is also can explain this magnetization data. So now, as I've shown you before, we have this increase of magnetoresistance only at like across the 120 Kelvin, and also the oscillation amplitudes, and all these, let's say, interesting properties happen at low temperatures. Now if I plot the magnetic fraction of the static C-axis aligned structure, this sets in exactly below 25 Kelvin at low temperatures. And then we have the two temperature scale. So this is a magnetic crossover temperature, and this is below which we get the static, quasi-static patches. So it seems that the slow, also we have the actual magnetic ordering above room temperature, the slow magnetic fluctuations, which would be at the rate of megahertz, is kind of detrimental for these topological properties, and you only get all the features as soon as you get really true static C-axis aligned structure. So after that, we thought, okay, can we really tune these different the patches or domains with a hydrostatic pressure? So one important aspect here is if you measure the moment size of the terbium manganese, there's no much influence. Okay, it's saturated because I think we get the static regime, but there's no much. So this animal soul conductivity is not really influenced by the moment size, but it's more influenced by this magnetic crossover at low temperatures. And this also distinct behavior here can be explained by probably distinct magnetic domain distribution, which can be created by different cooling of the sample and so on, combined with magnetostriction. So then what we did, we tried to tune the system with the pressure. And you see that at zero pressure, we have this two frequency, as I've shown you. This is the more like dynamic patches, and this is static. And then when you apply pressure, you promote this, So at 2.1 GPa, you have only the truly static C-axis aligned structure in 100% of the sample. So basically, with pressure, we can promote the, let's say, topologically active static state. And we can also increase temperature by 5 Kelvin, not so much. But to see this nice interplay between these two states is quite exciting. Okay, so to conclude this part, we have seen that we did also a lot of neutron diffraction on the sample. So we see that we have outer plane ferromagnetic ordering between manganese and terbium with slow magnetic fluctuations. However, then we see the fluctuations slow down below 120 Kelvin and forming quasi-static patches with ideal C-axis structure only below 25 Kelvin. And then it enhances in a volume-wise manner. So we saw the pressure of 2.1 GPa stabilizes C-axis structure in a whole volume of the sample, and would be nice to measure the topological electron structure under pressure, which we did not do so far. And so we see the low temperature magnetic crossover is coupled to this interesting low temperature topological phase of this material. And so we could exclude any incommensurate also K-vector from the small angle neutron scattering measurements. Okay, so now the last part of my talk will be on this time reversal symmetry breaking state in this 135 kagome superconductor. So I think previously there was a talk from Professor Wilson, and also Jashin gave a talk on this subject. I'm sure they did a lot of introduction and gave the students a lot of information. But now I will make a few introductory slides to motivate the MUSAR studies. So the system has the layer structure with this vanadium antimony layers, and the vanadium has the perfect kagome lattice and then there's two different sublattice of antimony. So one of them is like a graphene-like structure. And what was interesting that the Fermi level of this material is close to several saddle points and the Dirac points. It was also shown that the normal state band structure of this material has a Z2 topological invariance, which means that it also exhibits a topological surface state. And it's also shown that topological surface states actually go very close to the Fermi level below the charge density wave transition temperature, which I will talk about later. So interesting band structure, and this lattice, the kagome lattice, attracted a lot of attention at the beginning. But I think one of the first remarkable experimental result that made me interested in the system was that there is this giant anomalous Hall conductivity that was observed back in 2020. And you see that different from Cobaltine compound, which I was talking about during the first part of my talk. So this compound was coming from the intrinsic part of this. In this regime, the animal soul conductivity does not depend on the longitudinal conductivity. And so this is considered as an intrinsic behavior for the intrinsic part of the barrier curvature, or the intrinsic part of the Hall conductivity. While for this compound, you find this quadratic scaling between animal soul conductivity and longitudinal conductivity. And this was explained or interpreted as a skew scattering from the disordered spin clusters of the vanadium lattice. But then later on, from MUSR experiments, it was shown that there is no long range or even short range magnetic ordering. And also neutron diffraction showed that there is no long range ordering on this material. So the probably interpretation of these clusters was then had to be, was not probably precise, but the experimental result was the remarkable showing the large animal soul conductivity. So this motivated a lot of studies to look for the transitions, electronic orders in this system. And so the magnetic susceptibility as a function of temperature shows that there was a transition at 80 Kelvin, a clear anomaly, when the field was applied along the c-axis. And then there's some increase of the susceptibility at low temperatures. And this was speculated to be because of some electronic order at low temperatures. And then later on it was shown that the system is also superconducting with TC of about 1 Kelvin. If you have potassium, if you have cesium, it goes up to 3 Kelvin. And then later on, the STM experiments have shown that the system exhibits a 2x2 charge order, so isotopic charge order, which is consistent with a breaking of translational symmetry along A and B directions. And this is a Fourier transformation of the real spectra. And so they could see some kind of intensity differences in between these three the three charge order wave vector peaks. And these differences in intensity was denoted as a chiral charge order. And when you apply the magnetic field, then they can also switch the intensities of this different CQ vector peaks. So you can kind of tune this intensity by magnetic field. And I think Jashin talked about a lot about this during his seminar. But here I want to summarize this slide as saying that this was kind of a hint from STM results that there is time reversal symmetry is broken by charge density wave order. And this field switch effect was also found in rubidium system as well. So you have some kind of orbital currents that breaks time reversal symmetry. And this kind of unconventional charge density wave was also shown to open up the topological gap in this at the Dirac cones, and then could produce also the non-zero Berry curvature, and this could contribute also to animal soul conductivity. So this hint from STM that there is time reversal symmetry breaking charge order motivated and encouraged some magnetic probes to look for this time reversal symmetry breaking state. So there is different very interesting theoretical works that looked at some kind of the leading and subleading instabilities in this system and discussed different mechanisms for the charge density wave formation. And most of them say that basically TRS broken charge order with orbital currents is energetically favorable state. And you have different, ways, different types of orbital currents or chiral flux phases, and so on. So the very interesting paper was from the group of Leon Balens was saying that the real charge density wave is a primary order, but this kind of imaginary component which breaks time reversal symmetry can be induced by magnetic field. And if the energy of ICDW is close to this RCDW with small magnetic field, you can induce the TRS breaking state with orbital currents. And the state with this ICDW only exhibits a very tiny moments. And yes, so it might be hidden, but then if you have the right technique or with low moments, you might be able to see it. Okay, so as you know, the orbital currents have been suggested to produce the quantum anomalous Hall effect in this honeycomb lattice, or it was proposed to be the order parameter of the Sirtoge phase in the high temperature cuprate superconductors, and now also the proposal for orbital currents in kagome lattice. But the experimental observation of orbital currents or the signatures for orbital currents is a long-standing motif, both in topological and correlated materials. And so what we try to do is to use the Muon spin rotation for this topological kagome metal to look for any weak static or dynamic or fluctuating magnetism in the material. So this is the polarization as a function of time, muon spin polarization. And you see that there's no oscillation because we don't have long range order, but you clearly see there's some temperature dependence of the relaxation rate. And then when we apply a small field longitudinal, so we have here the muon spin, which is rotated by 60 degrees with respect to c-axis, and then we have these 4 different positron detectors. So if you don't rotate the spin and apply magnetic field along the spin polarization, you can completely decouple the relaxation rate. And this is a signature for static internal fields on the microsecond time scale. So we don't have fluctuations, but we have really a static internal fields at the muon site. Here I want to highlight one thing is that, so if you try to, so in this system we have the large, dense system of nuclear moments with large nuclear moments and large natural, the high natural abundance. So in that case we expect the relaxation rate to have the form of so-called Gaussian Kubo-Toyabe function. So the Gaussian Kubo-Toyabe function that reflects the field distribution at the muon site created by the nuclear moments. But you can clearly see that the red curve, which is a nuclear, so this is a Gauss Kubo-Toyabe function, does not fit the data well, and there's a big discrepancy if you look at the data from these forward-backward detectors. So it's clearly this response is anisotropic. And so you need to add the additional exponential relaxation rate, which we suggest that this is electronic relaxation rate. So this extra exponent is electronic, has an electronic origin, which is then also supported by the high field measurements. So we did other different functions, which gives slightly different functions, more complicated to fit a bit more complicated nuclear response, but we always get the additional electronic relaxation rate. So if I now plot the delta, which is the width of the local field distribution as a function of temperature and the exponential relaxation rate, so this is what we get. So you have clearly the increase of the exponential relaxation rate below the charge is the wave transition temperature, and which you can more clearly see here. And this increase of the relaxation rate means that you have kind of enhanced width or enhanced spread of the internal field distribution at the muon site, just below the charge wave transition. And then it continues at low temperatures, and across TC, we don't see much change. So it really continues into the superconducting transition. So this kind of increase is also followed by this non-monotonous behavior of the nuclear relaxation rate with this maximum here. And then you have some kind of shallow minimum, and then it increases again. So we have this non-monotonous behavior, which is reproducible also in rubidium sample and different samples of potassium. But so we clearly have this increase of the exponential relaxation rate. So we don't want to go into details, but if you do try different models, you always have the increase of the relaxation rate just below the charge density wave transition temperature. The increase of the relaxation rate is about 0.025 universe microsecond, which corresponds to the internal field strength of 0.3 Gauss. And this more or less the values which was also found in the famous TRS breaking superconductors on glutamate and few other TRS breaking superconductors. So this is similar field strengths. I think here is a bit higher, like 0.5 Gauss, but it is same order of magnitude. And also in these other multi-band non-centrosymmetric superconductors, this kind of behavior was observed. So this kind of, we have for the nuclear contribution is kind of shallow minimum. Here also in the superconductors, they don't see increase right below TC, but there is some kind of minimum and then increase at lower temperatures, which was explained in terms of some kind of complex chiral superconducting state and so on. But at least experimentally, this kind of minimum was observed in different TRS breaking superconductors. So to substantiate the zero field Muir measurements, we did also high field Muir experiments where the configuration is a bit different because here the muon spin is rotating around this the plane, and then we apply a field along the c direction. So we collect all the positrons by all these 16 different positron detectors. So here what we see in 1 Tesla, so you see that we have this kind of non-monotonous behavior. So in high field, we cannot distinguish between electronic and nuclear contribution. So here, this is similar to the one behavior we observe in zero field, but for nuclear moments. That's why we're seeing is mostly dominated for the nuclear moments. But when we increase the field, then we see a stronger, clear increase at lower temperatures, and we continue 5 Tesla, again bigger increase, and 8 Tesla. We have a very well pronounced increase of the relaxation rate at low temperatures. So this shows that at low temperatures in high fields, the relaxation rate is dominated by the electronic contribution, because the nuclear contribution does not change with field. So we make the electronic contribution stronger and stronger, nuclear stays the same. So we dominate here with the electronic response. And also this is so-called night shift, and this is more like a local magnetic susceptibility. We chose the increase, so this is a negative here. We chose the increase just below the charge density wave transition temperature. And so within this, at low temperature, we have some kind of peak. I don't exactly know what it's related to, but it could be some kind of related to some maybe nematic susceptibility, which was found for the cesium compound by Ilya Tselkovich and his group. But this one has to, do some more careful measurements at low temperatures and try to understand this. But at least there's a clear increase of the local magnetic susceptibility below charge density wave transition temperature. So compared to zero field in 8 Tesla, we have increase of relaxation by 0.15 inverse microsecond, which shows that there is a strong field-induced enhancement of the electronic response, and it's very clear. So with these Muser measurements, we provided the local magnetic probe evidence for this time reverse asymmetry broken charge order in this compound. And this means that the magnetic and charge channels appear to be strongly intertwined in this kagome superconductor. Since we know, yes, and if we do maybe 5 more minutes, 5 more minutes. So if we do the magnetic susceptibility measurements, you see always the charge density wave peak at the same temperature, but we see also here the increase of the susceptibility that somehow could be related to the same physics that we also see in the local magnetic susceptibility. But one important aspect here is that if you apply field along the in plane, there is no anomaly of the charge density wave. So you see it's strongest when you apply field along the z-axis. So magnetic response across the charge density wave is clearly anisotropic. And this could also maybe related to orbital currents, because the orbital currents are kind of coupled to the z-axis moment. They don't really create much internal fields, in-plane fields. And maybe that's why the effect is stronger when the field is applied along z-axis. At least the fact that the magnetic response is really anisotropic maybe points to the fact that there is some magnetic origin is coupled to the charge density wave transition. So for the last 2 or 3 slides, I want to show you, since we think that the charge density wave is somehow, unconventional, and there's some orbital currents involved in this formation, it's interesting to probe the superfluid density and the symmetry of the superconducting gap. So this we also do with muons, because we can shoot muons, a lot of muons in the vortex state, and then we can probe the field distribution in the vortex state, and from this we can extract the magnetic penetration depth and measure it as a function of temperature, which is then sensitive to the topology of the superconducting gap. So what we see is this is a normal state above TC. You have strong damping because of nuclear moments, but as soon as you enter in the superconducting state, you have enhanced relaxation rate because of the formation of the vortex state in the superconducting state. And you see the relaxation rate increases just below TC when you apply field along the plane, or if you do the along the z-axis, we have some anisotropy, high temperatures, but you still see the increase of relaxation. So overall increase of the superfluid density at low temperature below TC is small. And but you see this interesting 2-step kind of behavior within the superconducting state, and you have kind of linear, more or less linear temperature dependence. And recently, like for the last few days, we have been taking data in the dilution fridge, so we can see that this does not really saturate. This could point to some kind of nodal structure, but at the moment we cannot make a sharp statement, but at least it does not saturate as you would expect for S-wave superconductors. And we have a relatively large penetration depths. So when you apply 100 Gauss, you basically smooth out this behavior here. So it's not any more sharp, but you still have this two-step kind of temperature dependence. And it's also similar true for the rubidium compounds. So this is reminiscent of the behavior found in these well-known two-band superconductors, iron selen or this vanadium-3 silicon, where people see this two-step transition in the superfluid density. And this was explained with a very weak interband coupling between the two bands, which gives the still same TC, but this two-step behavior. So we also have a single TC, but two-step superfluid density. And so our result is consistent with more like a two-gap superconductivity on two different bands with very weak interband coupling, like in iron selen or in this vanadium-3 silicon. So the last slide is that we also, to compare this superfluid density of this material with other unconventional superconductors, I show this Uemura plot where the conventional superconductors are far right on the plot. So they have large superfluid density and very small ratio. So this material is very close to other unconventional superconductors like electron dot cuprates or the well semi-metallic state, the semi-metallic superconductors. And this is again kagome superconductor. So it's far away from the conventional superconductor state. So this means that this system is characterized by dilute superfluid, so low density of Cooper pairs, and the same true for also rubidium compound. So I think it is shows the features of unconventional and two-gap superconductivity, and we still don't know. We cannot. Could be nodal, but we don't know. We don't know yet. Okay, I will skip this. Yeah. So what we observed is enhancement of the internal field widths. It's sensed by the Muon ensemble, which takes place just below the charge density transition temperature. We see that we can enhance the electronic relaxation rate by magnetic field. We show that we have multi-cap nature of superconductivity with a small superfluid density comparable to unconventional high temperature superconductors. And we conclude that we have time reversal symmetry breaking charge order, which is intertwined with unconventional superconductivity in this material. So basically the general summary would be that I tried to convince you that topological materials can be studied in the bulk by local probe technique to uncover some aspects of coupling between the symmetry breaking order and electronic topology. So I'd like to thank you very much for your attention, and I'm happy to accept any questions.
Yeah, thanks a lot, Zurab. Very nice talk. Yeah, so Daniel, you have a question? Yeah, Dan Konsky.
Yeah, I have maybe a very simple for you question, but somehow I just mixed up. What is really the meaning of chiral charge density wave? Is it chiral in a plane somehow, or it is so that charge ordering pattern in one plane, and when you move to next plane, that's no change in the chiral pattern? What is really
as far as I know, the chiral within the plane. So when you go, but there's different theoretical proposals. You know, from MUSR point of view, I cannot say anything about the current structure, right? What we can only say that we have some weak internal fields just below charge density wave, which could be consistent with the currents created by the density, electron density. But I cannot.
That's actually the second part of my question also.
Yes.
I understand that current states, spontaneous currents like Varma or whatever, they indeed break time reversal symmetry. But what is really the relation between current carrying state and charge density wave? Are these related phenomena, or these are two different phenomena which just happen to coincide and come together?
Yes, so yeah, that's a good
really
question. So
what's simple physical picture?
Yeah, I think so. For the muons are not sensitive to, let's say, charge, right? Let's say charge density wave transition. Yes, but now there's two things. So when we do experiments in zero field muons, we see the increase of the internal field widths, but at the same time we see also change of the nuclear relaxation rate. And what is happening in zero field that you have change of the electric field gradient across the charge density wave transition, which would also change the coupling between the muon and the nuclear moments. So that's why we cannot really say clearly whether we have changed just because we have charge density wave, or we have changed because we have orbital currents. But when we apply high magnetic field, then we can exclude the change of the EF electric field gradient, because then the magnetic field is creating the quantization axis for the nuclear moment, so it's fixed. So only thing we can change is the electronic contribution, which would come from the orbital currents. And we still see that change happening at the charge density wave transition temperature, right? So we kind of favoring that orbital currents has the same onset, or whatever weak fields we see have the same onset as charge density wave, but I cannot say whether which one is it driving or which one happens first. So their kind of onset is the same. This is what I can say. I don't exactly know,
What's the size of the moment when you have a high field? I mean, you said
size
with half a Gauss.
In high field, in high fields, it is the moment size would be less than 0.1 μ, even smaller.
In high field, it's actually smaller. The order moment.
So
it should be larger, right?
It's a point. No, it's a 0.3 Gauss in terms of field, but in terms of moment, it would be 0.02 or something. Then in high fields, you have 6 times higher, so it's close to 0.1 μ.
Okay, Alu, you have a question?
I have a small one. I just wonder whether I caught correctly the situation, because the charge density wave, if I remind it, occurs at 170 K or something like that, while you see a magnetism at 70 K.
No,
so
the charge density wave
140 K.
System, no, charge density wave in this system is at
90 K, 90 K.
80 Kelvin in potassium, so 90 Kelvin is in cesium.
Okay,
so
then it means that the magnetic signal coincides with the charge density wave.
Yes, it has the same onset.
That's what he claims, yeah.
Okay, good.
So also, did you do magnetic field experiment for field in the plane and see what happens across the
Yeah, exactly. So with the MUSR setup we have on the instrument, because the crystals are very thin, and I cannot rotate the magnetic field, and we also cannot mount many samples like this. So only possibility I have applied along z-axis. But to answer, but that's why we did measurements of susceptibility as a function, in plane, and there we don't see any charge density wave anomaly, right? In plane, where is it? Yeah, here. For instance, when we apply field in plane, there is no change. While if you apply out of plane, and I think according to the Princeton, I think Jashin, if they apply field in plane, STM also does not see the change in intensities. It only see if you apply field along z-axis.
How does that reconcile with the orbital current picture?
Yeah, I think because orbital currents are in plane, right? So somehow they create a field which should be out of plane. So they're mostly coupled with the out.
No, but if you apply an in-plane field, I mean, what happened to the orbital current?
Yes, it somehow it seems, if this is because of orbital current, it seems that they are silent with in-plane field for some reason. I don't know why.
Okay. I have another question. So in your earlier talk, you talk about the phase separation in cobalt, tin sulfur, right? The just below the magnetic ordering temperature.
Yes.
How do you understand this? Considering the material has the same crystal structure, how can you have two different?
Yes.
How can you have two different magnetic structure? I mean.
Yeah, exactly. So the crystal structure we see the crystal structure is the same. But we never measured local structural distortions, right? So
you think the local structural distortion is slightly different between the two parts?
Yes. This would be my guess, and there is a strong coupling between structure and magnetism, because when you across the magnetic transition temperature, you have change of this Gaussian and Lorentzian widths in the neutral diffraction pattern. So you clearly see that somehow structure is coupled to this magnetic domain.
Oh, I'm sorry, there are a couple of questions. Chandra Verma has a question from, are there single crystal available to do polarized neutron scattering to determine geometric time or some? Yeah, so Chandra, we're going to try this, hopefully in the next couple of weeks, yeah.
You do have decent single crystals available?
Yes. I mean, well, we're gonna try it with your friend.
Okay. Because this would be a much easier experiment than in the cuprates.
That's what Philip convinced me.
Yeah.
Yeah.
Okay. Thank you.
So another question from Chanton said you had a chance to do a moment direction of the cobalt doped compound. What does MUSR say about direction of the magnetic moment in the 135 system? It's along C, right? Did I remember correctly?
The local field in this, so we see.
No. He's asking, what does MUSR say about the direction of the magnetic moment in the 135 system?
The magnetic moment we cannot say without really knowing precisely the stopping site, but the internal field seems like to have both components along C and in play for this potassium.
Yeah, along C.
So it really depends on, both. For rubidium, the electronic contribution seems to be higher.
Okay. Are there any other questions?
Yeah, Pension, can I follow up on this?
Yeah, sure, absolutely, Chimal.
Hi, Zurab.
Hello. Look.
Yeah, so the same, just follow up on the C direction versus AB plane. Yeah. Is there some further quantitative information about how big? I guess I'm more interested in the zero field limit.
Yes, zero field MUSR, right?
Yeah.
Yes, here. So this electronic contribution from this forward backward is overall higher. So they clearly also anisotropic in above the charge density wave transition. They are not really coinciding. But the increase below CDW is more or less the same strength for both up, down, and forward, backward. But the fact that it's anisotropic, sometimes the nuclear contribution would also be anisotropic because you have different hyperfine coupling between muon and nuclear in this anisotropic coupling tensor. But the increase below CDW is more or less same for both orientations. There is no much different.
Okay, thank you.
Welcome, thanks.
Okay, are there any other questions for Zurab? Okay, if not, I mean, students, are there questions? And they always try to encourage students to ask questions, but it's very tough.
Maybe nothing was clear.
Well, everything's clear, right? One of the two.
Peng Chang, I wanted to say that.
Hey, Chandra.
Hi. One of the experiments done by Hassan with Dr. Guguchia, I think, observed that chirality in the charge density wave changes direction with the magnetic field.
Yes. That's from the STM. I mean, actually, did you see that?
No, it's really from the detailed analysis of the Bragg peaks he sees in diffraction.
From X-ray?
I'm not sure it's STM.
No, it is. I think it's. I mean, Zurab can correct me, right? It is STM measurement, right?
But what I wanted to, I have maybe forgotten the details of the experiment, but that experiment, I looked into this last week. There was a proposal made by Jiangping Hu on a specific magnetic pattern. Specific magnetic pattern of currents, and there are about 189 different possible patterns. So it's very nice that there's a specific pattern that Jiangping suggested, which I found is consistent with the Hassan and the Guguchia measurements that I remember, as well as the fact that inversion is not broken. There's no second harmonic generation. So I think with neutron scattering, that makes a very specific prediction as to where to look. Otherwise,
okay. Well, let me check out. I have not seen the Jiangping's paper. I have not checked the web.
Okay. Otherwise, one can go crazy. There are
I also need to check. Yeah. Because for this, we also need to do this precise muon stopping site calculation, and then to check, precisely this whether this specific structure of orbital currents would match also the increase of relaxation which we see.
Incidentally, this can also be tested by doing angle resolved photoemission with right and circular polarized photons and looking at the difference. There are very there would be very specific predictions for that.
Yeah, yeah, that's right.
Chirality means the reflection is broken everywhere.
Exactly, yes.
That's specific prediction. Is anybody trying to do those experiments?
No, I don't think, I don't know.
No, I'm sure there's some APAS group. There's so many APAS groups working on this stuff. Yeah. Okay, but your suggestion is very good, Chandra. I mean, I take note. But jumping's prediction. I'll search on the archive to see what he says. Yeah. Okay. Yeah. Thank you very much. Yeah.
Okay. Thank you very much.
Yeah. Thanks a lot, Zurab. Yeah. So if there's no further questions.
Thank you very much for the invitation. And
thank you. No, it's great.
All for joining.
It's recorded. Yeah. But so hopefully we'll get some impact on this. Yeah. Thank you very much.
Thank you.
Yeah. Bye.
Thanks a lot. Bye-bye. Thank you, everyone.
Bye.
Bye, everyone.